Okay, let's look at a second example. Let's see how to record data when we're exciting the speaker with a sinusoidal voltage. In other words, we're producing a pure tone. Okay, I'm going to start the data recorder. And now we'll turn on the sound source. There we go. And you'll notice the first, the sinusoidal wave, that's the microphone signal. And you notice also there's a square wave as well. That's the trigger signal from the function generator. So we're measuring them both. Okay? Very good. On the function generator, we can change the frequency of the source and watch what happens to the sound inside of the sound tube. And here I'll start stepping up in frequency in units of 1 hertz. Do you notice the amplitude is changing? We've just tuned through some kind of a peak. Let's go back to the peak point, somewhere around here, right? Now notice at this point, the wave looks very distorted. It's flat on the top and flat on the bottom. What's going on there? Well, it's no great mystery. What's going on is the sound is simply so loud that it's overloading our microphone amplifier. So we should turn down the volume of the source until we're not overloading. Let's do that now. There we are. Okay, and now if we go back and carry out our experiment, going up in frequency, you can see it goes down, and on the other side as well. So this frequency seems to be the peak. That's a resonant point, a point where the frequency of the sound wave matches the boundary conditions in the sound tube, and we can accumulate lots of acoustic energy in the sound tube. Okay, and one of your goals is going to be measuring the frequency of these resonant modes. Okay, now in this case, we were able just to eyeball the amplitude of the signal and then adjust the frequency to optimize. But what if we wanted to have the system measure the amplitude of the signal? This will be important for the last task that we want to do, which is measuring the wave function of the sound wave in the tube. But we could be using it for finding the resonant part as well. Well, since we've recorded the signal, we can also measure the amplitude by looking at the signal that we've just stored. That's done here. You can't see it easily in this video, but there's a box here which displays the amplitude of the sound wave, okay? In this case, 1.65 volts. And it's doing this by essentially fitting the sine wave to find its amplitude, okay? And when it does the fit, it doesn't have to guess at what the frequency is because it measures that from the trigger signal, okay? Now, there are a couple of things to note about this. First, the measurement will be more accurate if we have a longer string of data. So instead of taking only a few hundred points, we should have the system record several thousand points, maybe 10,000 points. Now this amplitude number no longer shows any fluctuations, more accurate. The second point is more subtle, and it has to do with the way that we're doing our curve fit. So for a curve fit to a sine wave, amplitude is one variable, frequency is a second, and the third is phase. We're not fitting to the phase. Instead, we're assuming that the phase is equal to the setting of this knob here, currently set on 0 degrees. In that case, the phase of the sound wave would match the phase of the trigger wave. But there could be a phase offset, and so we might adjust this in order to check. So if we adjust this, we can look for another point where the signal is as positive as it can possibly be. And then we find it here at a phase of about 320 degrees, or in other words, minus 40 degrees. So the sound wave actually was displaced in phase by about 40 degrees from the source for this particular point. This is a setting which we might only have to adjust once, but now we've adjusted it. And it didn't make too much difference for what we're going to do. Okay, I just wanted to show you that. Let's stop.